Amanda, should I wait for you to give me the official okay?
If you want to start whenever, we're all
Okay.
set up.
Okay, then great. Okay, everyone. My name is Marie. I'm a tutor for Leland, and this lesson, just so you guys know, I one of my favorite things to cover is number properties. There are two things that people usually say that they dislike the most, and those are probability and number properties. And those are my two favorite things to teach. But number properties is the basis of everything. It really is how I like look at numbers, and I start every single class I've ever taught in my life, from high school to anything. I always kind of start with the way that I approach numbers. So this one makes a lot more sense than doing probability because I'd have to like do this entire lesson before that one. So before I launch in, okay, and basically what I'm just trying to do with this is like give you guys a snapshot of a real lesson of how I start off, so you can see a little bit of like what's in the special sauce. And but before we start, I kind of want to know just where you guys are, like who my audience is. So first question is, do you think you're taking the GMAT or the GRE? And or you don't know and you don't care. Also, when are you applying? Do you think it's going to be round one this year, round two, 2027? Just let me know who my audience is. And put this over here. GRE, okay, great. Okay, cool. Okay, and then other questions I just basically have about your respective test. And just like, even if I don't, it doesn't matter if I remember which person said GMAT or GRE, but on a scale of 0 to, or like maybe like 1 to 5, on a scale of 1 to 5, um, how familiar are you with the content or the question types? And I don't mean that you know how to do everything, but maybe you kind of know that they look, I don't know, like the SAT, ACT, or you've seen them on a, yeah, 0, 1, I'm sorry, I keep changing my scale. From a 1 to 5, how familiar are you with the test? I guess that's the best question. And she met in a couple of years. Cool. Okay. Okay. Um, okay, just starting to prep. Okay, cool. Okay. Um, okay, great. So again, let me tell you a little bit about like my intention for this. Okay, well, first of all, you can see a little bit about me. I tutored from Kaplan for a very long time ago. I don't think that I don't even really associate myself with Kaplan because it was like many moons ago. And I since then went to grad school. I was a high school teacher. All the time I was a high school teacher. I always did test prep. And honestly, this is my true love. I do love teaching high school and teaching. I like being with like high school kids, but I think that what I like about this is that I really get people to think and become problem solvers. And I don't really just say like, okay, do this kind of problem and do it 15 times in a row. And then I like put all the curveballs. I have to sort of teach you how to think about curveballs and how to think differently. And the only way I really can do that is by like making you look at numbers differently. So that's really what this lesson's about. I was also going to just ask like if does anyone have any idea about what do you want to get out of this? Like, why did you sign up for this? Just to get a taste of what this looks like, or any specific questions? If you could throw that up there, and then I will start. I'm going to scroll through all these nice things that this is something my nice student Cole said about me. He got a 760. He was very bright. And let's see, let me just hit these. Oh, okay. Also, I have a code that I'm supposed to tell you guys about in case you're interested at the end. But this is my intro 6 code. Usually, a lot of times I do meet with students and we talk about private tutoring. And sometimes they start off with 6 hours before they sign up for like, sometimes the courses are 36 to 48 hours, or, depends really. But those are kind of like the full scope of people who have done nothing. And this is my other student who got a 780. So yeah, I'm gonna let that one linger. Okay. Here we go. let's get started. Okay, I want to see. Okay, cool. Okay, so first I am going to go through some of the basic stuff, but if you guys think this is easy, I promise it will ramp up to super hard questions by soon enough, okay? First day. Okay. Okay, the first thing I will try to go a little bit quickly, but if I'm losing anyone, just, let me know. Okay, so first thing I always ask people to do is please write the first 10 prime numbers. I'm going to give you guys 10 seconds to think about this. Start rating the first 10 prime numbers. And I don't mean the ones under 10. I mean, try to get to 10 of them. Okay, I'm going to start. Let me get my more appropriate color going on here. The first one is 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. I'll just address some things. Sometimes people say 1 is not a prime number. I'm going to explain why. Sometimes people forget 2. 2 is like a celebrity prime number, okay? It's the only even one. It's what makes numbers even. Later on, I talk about it being a contaminant because it takes pure numbers. Well, if you have a 2 in your chain, it will make it even. And if you have 1, 2, 2 2s, 3 2s, it makes it even. So I have this idea about pure numbers, but that's kind of a separate topic. And then I'm going to explain prime numbers are like building blocks. There are the building blocks of all other integers. So first time I'm going to talk a little bit about like prime factorization. So I think of and this concept of number caterpillars, I'm going to explain what this means in a second. Okay, let me slow down here. If you take the number 12 and you were to do a factor tree, you have 2, 6, 2, and 3. Okay, so here's your prime factorization for 12. 2 times 2 times 3, which I'm going to write over here. And when this idea first took shape, I would explain to my students, this back in my SET days, that I'm like, prime numbers are like elements on the periodic table. They are these indestructible or unbreakable, you can't break them down any further, to these particles, just like elements. And just like H2O is a water molecule with an oxygen and 2 hydrogens, 12 is a molecule with 2 2s and 1 3. And I called them number molecules for a long time. There was a time when I was teaching middle school and no one wanted the molecules was not cute to them. So then number caterpillars took over. And then I would draw them like this. So this became my thing, number caterpillars. And later on, and this is going to seem like a silly assignment, but I do this, I'll show you what I do with make my students do. I make them color them in. And they do the prime factorization of every single number from 2 to 100, okay? Because look, there's no 1 here because no 1 is a prime number, but every single student will do this for me. Now, this is a student of mine from a couple years ago who had an iPad. So because she had this infinite number of colors, I've always used hers. And I just like to mention that she got into Harvard and she will be going there deferred. So starts in, I think, next year. Anyway, okay, so back to this. 18 is, make sure of these colors, right? 18 is a 2 times a 3 times a 3. 30 is a 2 times a 3 times a 5. And that's just, I'm just doing factor trees for all of these. And then I'm going to color them in. And I want to go back to why 1 is not a prime number. Okay, so if you think about colors that I use here, this one. Okay, so there's something called the fundamental theorem of arithmetic, and the fundamental theorem of arithmetic. You can look it up on Wikipedia. But basically what it says is that every integer has a unique makeup of prime numbers, and that unique prime number, that unique makeup, it goes back and forward. In other words, like 12 is made up of 2 2s and a 3. And if you took 2 2s and you multiplied by a 3, you would get 12. So they go back and forward. And that's the unique chemical molecular makeup. And that's why 1 can't be a prime number, because if I put a 1 here and another 1 here and another 1, I mean, it's still 12. How many am I supposed to add? 1 is not a prime number. It's like the lack of prime numbers, okay? Sometimes I explain it as, yeah, the empty set. Hold on, let me find my, okay. So anyway, let me go over the concept of greatest common factor, lowest common multiple. I want to make sure people are clear on this before I get into harder topics. First of all, let's go over definitions. Factors. Factors fit inside. Okay. Factors are finite. So instead of giving you a definition, I just want to give you an example. Factors of 12. You had to find all the positive unique factors of 12. Start from the outside inside. 1 and 12, 2 and 6, 3 and 4. And here you have 6 positive unique factors of 12. This over here is the number caterpillar. This is the prime factorization. The caterpillar helps you find a lot of things, but the question is almost never about the caterpillar. It's always about like a question like how many unique factors? There's 6 here. Later on, when the problems get harder, we're going to use this. Multiples of 12, multiples are infinite. Okay. Sometimes I used to say multiples are more, but that's kind of misleading. 12 times 1, 12 times 2, 12 times 3. This is going to go on forever. I'm putting one more here. This goes on for infinity. And technically, it could be 0 and it can go the other way. You don't really see that too often, but it does come up in like, there are rules for divisibility, how to tell if a number is divisible by 4 or divisible by 11. And it's important to know that 0 is a multiple of, 0 is a multiple of any number. You can't divide any number by 0, but you can always say that 0 is divisible by any number. Okay, so let's go over the concept of greatest common factor and lowest common multiple. So we said greatest common factors fit inside. So we're talking, I tried to use these 3 numbers. So this would be something that maybe you guys like already know or you're looking up, and because I'm going to try to find the greatest common factor of 12, 18, and 30. But I'm going to show you a way that I learned when I was in middle school, and it stuck with me forever, and I've definitely made it harder. So, but let's just go over. So if I'm doing the greatest common factor of these numbers, 4, 8, and 48, greatest common factor squeezes that way. So the greatest common factor between these 3 is 4. And I'm trying to illustrate because people do some silly things here and they like lose the perspective of what's going on. But this number cannot be bigger than the smallest number that it is trying to fit into. You're saying it is the greatest common, fits inside all 3. The lowest common multiple is squeezing from the other direction. You want the smallest number that all 3 fit into. So this would be 48. Okay, all 3 of these numbers fit into 48. 4 fits into all these 3 numbers. They push from opposite sides. We never look for the lowest common factor because, well, that would just be 1. We never look for the greatest common multiple because that would be infinity. I mean, the infinity, like for example, we could say all 3 of these numbers fit into 48 trillion. Okay, so we're always asking for greatest common factor and lowest common multiple. Okay, now if I'm trying to do the greatest common factor of 12, 18, and 30, this is again what I learned, and I'm doing the color coding because when I do it with more numbers, it gets more complicated. But if I want the greatest common factor, I'm saying like, what do they all have in common that all fits inside? And visually, I see that they all have a 2 and they all have a single 3. Okay, now I just want to make a point that if this one had another 3 and this one had another 3, I would say 2, 3, 3. Like you can double up on the same prime number. But since I don't, let me go back. I'm going to need this picture. Since I have it exactly like this, my greatest common factor is 2 times 3 or 6. Okay, I'm clean this up for the next problem. Okay, so 6 is the greatest common factor. Hopefully you just think about that. You're like, yeah, okay, 6 definitely fits into 12 and it fits into 18 and it fits into 30. The lowest common multiple of numbers this is what I call the mama caterpillar. And the mama caterpillar is like, she needs all of these kids, the 12, the 18, and 30 to like fit inside. And this is what I was trying to I'm going to show something over here. See, multiples of 12. I was trying to illustrate something over here when I started writing all these. But 12 is a multiple of 12. 24 is 2 times 2 times 3 times 2. 36 is 2 times 2 times 3 times 3. 60 is 2 times 2 times 3 times 5. And what I'm trying to illustrate is that if you are a multiple of 12, you must have the pieces of 12 inside, even the very fewest pieces, okay? 12 is a multiple of 12. Ignore the 0. Let's not talk about that technicality now. I don't want to get into it. But 60 is a multiple of 12, so it has 2 times 2 times 3 in it. So now when I'm building a multiple of all of these, I have to follow those same rules. I have to make sure that all of these numbers fit inside it. But I also want to keep this mama caterpillar, I want to keep her load lighter. So I don't want to add extra numbers. I want to keep it the smallest number. So when I look at this, okay, and imagine like I don't know how many circles, I'm just putting a bunch up here. What I think of is I usually go with the longest caterpillar, but they're all the same length here. They're all 3 long. So I could start with any, maybe just start with the 12. For 12 to fit inside the mama, it needs to put 2 2s and a 3. Okay, so this has been like picked up. Now we go to 18, and 18 needs a single 2, which I have, and it needs 2 3s. There's already 1 3, so I'm going to add another 3. Now I have 2 2s, 2 3s. The 30 requires that I have a single 2. I have it. A single 3. I have it, but it also requires a 5. So now I have constructed the lowest common multiple between these 3 integers by looking at their prime factorization. It's always about their prime factorization. When you multiply numbers, especially on these tests, these 2 tests, the GMAT, GRE, really love to hone so much that like we work in a base 10 system. That's a favorite thing to, I don't know, it just comes all up all the time. So you should look for a 2 and a 5, which is 10, and then multiply the rest. 2 times 3 is 18. So the lowest common multiple is 180. Okay. And yeah, okay, that is the lowest common multiple of 12, 18, and 30. Okay, now I'm going to do 1 or 2 more problems and come back to this, and then I'll show you how they can apply to like harder problems on the test. Okay, so let's say I need to find all the factors of 180. Now, this isn't really like a question you're going to get on a test, but you might need to be able to rattle these off really quickly for some other part of a question. So the first thing I would do is and I always say, like, if you see, I'm going to call this the buzzwords for number caterpillars. If you see words like factors, divisors, multiples, divisible, primes, integers, or product of integers, a lot of these words. And also a lot of things, like a lot of another chapter that everyone does not like is roots and exponents. And roots and exponents, and these two are, I mean, they're like cousins. They could not get any closer. Everything that I love roots. Roots and exponents is, when I say I love it, it's not that I like it just myself, but I think I like teaching it to people because it should become easier almost immediately after you look at it, things like this. But roots and exponents are, yeah, closely related to number caterpillars. So these words, everything here kind of tells you that you should probably caterpillar a number, meaning you should probably do the prime factorization of something that you're looking at. Okay, so find all the factors of 180. We just had 180 in the last problem. I'm going to caterpillar that number. I see the word factors, so that's my idea. 180 is 10 times 18, so this is 10 times 18. 18 is 2 times 9. Okay, and there's my caterpillar. Okay, let me color code this. So this makes it easier to see. Okay, so start with outside in. 180. Okay. I know that 2 goes into 18 9 times, so 2 goes into 180 90 times. 3 goes into 18 6 times, so 3 goes into 180 60 times. What about 4? Does 4 go into 180? Yes. I mean, yes, no. Everyone think about it. I don't want to hear it, see any yeses or nos because I know that, like, someone's going to know it immediately and someone's not. So everyone think about, does 180 go into it? And then the next question is how many times? And then I'm going to have a big reveal that usually I'd say 95% of people think is enlightening. Okay, so the answer is yes. 4 does go into 180. And some people go, well, yeah, it's like half a 90. So it goes in 45 times. And a lot of times when I'm working one-on-one with students, I watch them because I see them go like this. Yeah. And if I see them go like this, then I know they did division. And I don't do division. The way I look at it is I say, okay, 4 is 2 times 2. And I see a 2 and a 2 right there. So I do know that 4 goes into 180 and it goes in this many times. 5 times 3 times 3. 5 times 3 times 3 is 45. So that's how I know how many times 4 goes into 180. I do not do division. I multiply up. If 5, oh God, what did I do? Okay, I'm never going to be able to fix that. This is like some program for graphic artists, and every once in a while it glitches on me. I have no idea. I've just basically been in here forever. Okay. So 4 goes into 45. 5. We know 5 goes in. Most people's just going to know because it ends 0. But if you want to know how many times, just hold the 5 away and then multiply 2 times 2 times 3 times 3. 2 times 2 is 4. 3 times 3 is 9. 4 times 9, 36. Okay. 7, 11, 13. Let me like do this for a second. Okay. 6, we should know that 6 goes into 18 3 times, 6 goes in 180 30 times. Then I usually go to 7 go into it. The answer is no. And the reason is there's not, sometimes people go, there's nothing you can multiply to be 7. And I'm like, yes, because that's the definition of a prime number. It's one of those new elements. It's like, hydrogen or something, and it's just not in your molecule. So 7 is not in there. Next question is 8. Does 8 go in there? No, but kind of a different reason. Okay. 8 doesn't go in because 8 is 2 times 2 times 2. 8 needs 3 2s, not 4 2s. I'm not saying it like that. I'm not saying 4 times 2, but I'm saying 2 to the third power. 8 needs 3 2s. So, and we're missing a 2. But you could get a question like 180 times x is divisible by 8. And if you did something like this, 180, let's say I said 180 times 8 is divisible by 8, and I have to say something like x is an integer. Otherwise, it's not fair. And I want to know what is the smallest integer that x could be. Going back to this, I would know that 180 is 2 times 2 times 5 times 3 times 3, and this is 2 times 2 times 2. And here's x, this unknown. And if I want this to be divisible, when you say that something is divisible, you're saying that at the end of the day, like that it's going to end up with 1 on the bottom. That's why it's not a prime number. It's like one is like the lack of prime numbers. So I'm going to cross off 2 here, and I need this 2 to disappear. So x has to be 2. I'm sorry, x has to be 2. The smallest thing that x could be, if x were 2, then I could say that 180 times 2, aka 360. 360 is divisible by 8. And it's divisible by 8 45 times. 5 times 3 times 3 over here. And you would get 45 over 1. Sometimes this is a big deal for my students because we get these really complicated questions that say, if blah, 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 blah is an integer. And I'm like, what does that even mean? And that's usually the biggest, that's part of the problem. Like we can't figure out like what the question's asking. And the question's asking when you're saying if something is divisible by something, or if something results in an integer, what you're saying is that the fraction, all the pieces on the bottom, all the prime numbers on the bottom got canceled out by pieces on the top. And now there's nothing on the bottom except for a 1 just holding that spot. Okay. And therefore you have an integer. Okay, moving back here. So 8 is not in 180 because there's not enough 2's. 9 definitely goes in. You know 9 goes into 18, but 9 you can see right there is 3 times 3. And 9 goes in this many times, 20 times. 10 goes in 18 times. 11 does not go in because 11 is a prime number and it's not there. 12 is 2 times 2 times 3. We have 2 times 2 times 3. What's left over? 5 times 3. So 12 goes in 15 times. And 13 does not go in. 13 is a brand new color. It's a new prime number. 14 doesn't go in because 14 needs a 7. We already know that 7's not in there. And right here we have all the different, this is like a systematic methodical way to get all the positive unique factors. Just going to count them. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 times 2. There are 18 positive unique factors of 180. Okay. And now in my class, I teach this, like there's a trick to figure out, to look at a number, to do the prime factorization and to figure out how many factors are in a number. I usually don't do that in this lesson because I do some really hard stuff with that that sometimes gets people upset. So I didn't want to do it in a lesson like this where I might need some interaction. But moving on, I have some other stuff I want to do. Oh, first, let's do this. I want everyone to take some time to find the greatest common factor and the lowest common multiple of these 3 numbers. And so if you're just popping in now, if you have no idea, if you're catching up and you want to know what to do, the very first thing I ask is do the prime factorization of all 3 of these numbers. Yeah, just do that. And then you can probably like follow along. While people are working on this, if anyone has any questions that they want to put in the chat, my guest. I like the people, I liked how I tried to keep it a 1 to 5 scale on what people knew. And still, I got some zeros. So cool. Back the trend. Okay, I'm gonna just start doing some prime factorization. Just make sure you guys are, and then I'm gonna take a break so that you guys can keep going, working on the problem. But to remind you, we are trying to find the greatest common factor of these three numbers and the lowest common multiple of these three numbers. And I'm gonna give a hint. The greatest common factor, that's Nicholas, I see what you're saying, but I think the Leland people will send it to you. It has to be like through something you signed up for. I personally won't, but okay, yeah, someone's responding. Okay. Greatest common factor. The number is going to be under 50. Okay, and the lowest common multiple is going to be greater than 1,000. So if you're getting a really big number, that's normal. Okay, I mean, I did like 12, 18, and 30, just sort of so you could have like some frame of reference of something that you could click with, or at least follow along with. But now I'm going for like things that you might actually see. So 96, the prime factorization of this, you should have 5 2s. Okay, so 2 times 2 times 2 times 2 times 2 times 3. If you prefer to write that as 2 to the 5th, 3 to the 1st, be my guest. I like the visual, and yeah, I see it like this, but it's also because I always see it like this. 72, 2 times 2 times 2 times 3 times 3. And 60 is 2 times 2 times 3 times 5. Okay, fixing those again, let me remind you, I just want to give everyone else another shot at this before I start making like, follow-up problems with this. So to find the greatest common factor, you are finding the greatest common fits inside. So look for the greatest amount of stuff that fits inside. The greatest common factor is going to be smaller than 60. It's going to be smaller than 50. I already put it up there, but it has to be smaller than the smallest number. Or at least it could, 60 or smaller on technically. And the lowest common multiple is you're trying to find a number and make a number. That's the one that sometimes is confusing, but that's the mama caterpillar. That's the one where you're trying to make a number with a bunch of circles and you want all of these pieces to fit inside. So you put all of these pieces in those circles, but you don't want any extra circles. Okay, and when you think you have an answer, just put got it in the chat instead of actually putting the answer. I just want to know how many people think they're comfortable with it. Okay, cool. There's enough. Okay, greatest common factor. They all have 2 2s. They all have a single 3. The greatest common factor is 2 times 2 times 3, or 12. Okay? The lowest common multiple is the thing that they all fit inside. So I really look at the longest one, and the longest one, I'm also going to put them over here. Sometimes people prefer to look at it like this. 2 to the 3rd, 3 squared. 2 squared, 3 to the 1st, 5 to the 1st. What you're saying is if all of these numbers have to fit inside, 96 is really the longest. And the reason it's the longest is because it has so many 2s. But for 96 to fit inside this number, I would have to have 5 2s. So 2, 2, 2, 2, 2. Okay, that makes sure that all the 2s from 96 fit in. 96 also requires that you have 1 3. I'll put that on there now. Okay, so 96 is now in the number. But I need 2 3s for 72. So I'll put an extra 3. I don't need any more 2s because I'm covered. And then when I get to 60, I'm covered for 2s, I'm covered for 3s. I just need an extra 5. Okay, so now this chain, and remember what I told you before, I would take the 2 and the 5. That's 10. I'm just going to hold it aside over here and just go times 10 so I don't forget about it. And then, I'll tell you, like, there's little things that I correct students on, and one of them is like climbing. I don't like when students go 2 times 2 is 4, and 4 times 2 is 8, and 8 is 16. Try to go a little faster by like going in between. So 2 to the 4th power is 16, 3 squared is 9. I'm doing 16 times 9 times 10. And then I do teach double digit multiplication. Let me just do single right here. But if I was doing 9 times 16, this is how I do think of it in my head. I think here's my 16, okay? So 9 times 10 is 90, 9 times 6 is 54. I add these together, I have 144. Now I'm going to multiply that by 10, so I have 1440, okay? That is my final answer for the lowest common multiple of 96, 72, and 60, okay? Now, I was just going to say, this is another thing I teach, double digit multiplication. If you're doing 23 times 17, instead of doing it with all that carrying stuff that you probably learned in school, this is like the area method, and it's a lot like foiling, and I use it for like a zillion different things, not just for this kind of stuff, but like for factoring things. There's a lot of different patterns, and I like this way because it shows you a lot of stuff that's important for these tests. So, hold on, I'm a compulsive eraser here. So 23 times 17, okay? 23 times 17. 20 times 10 is 200. 20 times 7, 140. 10 times 3, 30. 3 times 7, 21. Okay, I like this way more just because like you add things and it's easier to add a bunch of zeros. Like I see, I could just go 200, 170, and then 21, and 391. Okay, it seems much easier than anything with the carrying. But there's another thing that this illustrates. Okay, it illustrates that when you are looking at a 23 times, sometimes I do this when I'm like going really, really fast on problems. If this is something I have to figure out, I just am like, what does it end in? And I know that 3 times 7 ends in a 1 because 3 times 7 is 21. Okay. And the reason this number ends in a 21 is because these will always, the units digits of the original number are going to be what determines the units digit of the resultant number, okay, of the product. So as you can see, like 20 times 10, everything was a bunch of zeros, zeros, zeros. So right here is the only way that you can do that. So even if you have something like 318 times 72 times 19, at the end of the day, it's going to be 8 times 2 is 16 or 6. 6 times 9 is 54. So this is going to end in a 4. Okay, that's what I'm illustrating here. Now you just learned something about units digits. Okay, so that's more of a number properties thing, but there you go. Okay, where was I? This 1440. Okay, so we had these numbers. We had 96, and 96 was 2 to the 5th times 3 to the 1st. 72 was 2 to the 3rd, 3 squared. And 60 was 2 squared, 3 to the 1st, 5 to the 1st. 1440, I'm going to erase it and remind you. 1440 was 2 to the 5th times 3 squared times 5 to the 1st. And we know that all three of these numbers that this is the lowest common multiple. So that means that every single one of these numbers fits in there. So now let's figure out how many times, okay? And we're going to use this. So I want this to come like some full circle moments here. Double click around here. Okay, let's see. These are 2s, 3s. Okay. So 1440, I want to know 96 times what number gives me 1440? Okay. And I'm trying to kick up to the next problem. So I'm just going to show you how this works. 96 times, I'm trying to figure out what's missing here. Okay. I have 5 2s over here. I have 5 2s over here. I need a 3. There's 1 3 here. I need another one, and I need a 5. So this is like, I need a 3 times 5 to make the whole chain. So I just learned that 96 times 15 is equal to 1440. Okay. 72. What's missing from this? 72 is a little bit easier. Maybe you can see the relationship between 72 and 1440. But 72 needs 2 2s. Well, this is all 1440. It needs 2 2s and it needs a single 5. Okay, so 20. So 72 times 20 equals 1440. And hopefully that sounds like it makes sense because 2 times 72 is 144. 60 times what? Okay, I need 3 more 2's. I need another 3. So 2 to the third is 8. 8 times 3, 24. Okay, there you go. So now I'm showing you like how all these numbers go together. Okay, now I have a problem that I made up about 20 minutes before this class, but I love it. So hopefully you guys like it. Okay. Okay. This is more of a GRE problem, only in that it's like more than one answer choice is possible. Okay. So let's see. 4 is the greatest GCF of X and 20. 6, that's your first fact. 6 is the greatest common factor of X and 18. Which of the following can be values of X? Can be. Okay. I'm just going to label them A, B, C. Okay, when I said it's a GRE instead of a GMAT, it has nothing to do with level of difficulty because it's hard, okay? But in the GRE, you are allowed to select multiple answer choices. And the GMAT this is just not a question type. It's either, multiple choice where it's like one of these, or you're going to do well, data sufficiency is really more in data insights now. But anyway, multiple choice for math. So why don't you guys think about this for a second because it's good. If I'm going to give any hints, I'm going to give any hints. I'm going to say caterpillar, everything that you see, first of all, so you can follow along later. But you're going to try to figure out like what X must have and what X cannot have. And I'm going to give a couple minutes for this one because it's so when you do think you have it, um, say got it again. Cool then. Nice. Okay. Does anyone need more time? And if you like more time, speak up. It's totally okay. If not, I'll explain it. Okay. Let's give some people a little more time. And I do want you guys to try. If anyone wants a hint, you can ask for a hint. Okay, I'm going to start the problem. Here's where we go. Okay, if I'm told that 4 is the greatest common factor of X and 20, what I know about X is that it has to have 2 2's in it. Okay, it has to have 2 2's because the greatest common factor between X and 20 are the 2 2's. And what I also know is that X does not have a 5 in it, because if X had a 5 in it, then I wouldn't say that 4 is the greatest common factor of X and 20. I would say 20 is the greatest common factor. So when you say 4 is the greatest common factor, you're saying those are the only things that are in common between 20 and X. And so let me back up here. So what I've now learned is that there is no 5 in X. Okay. Okay. That's what I learned from 20. Now I go to the 18. And it says 6 is the greatest common factor of X and 18. So I know that, let me this is like a little bit irrelevant. I started doing this because I have extra time. But if I was really thinking about it, I'm looking at 18 and I'm saying 6 is what they have in common. So they both have this. Okay, now I already knew X had a 2. So I'm going to put another 3 there. And what I have learned is that X has a 3 because I already knew it had a 2. Great. But I also know it doesn't have another 3. Okay. Like maybe I should put like X has 1 3 max. Because again, if it had 2 3s, I would not have said 6 was the greatest common factor. I would have said something like 9 is the greatest common factor of X and 18 because I know X already has a 2. So here's what I know that X has for sure. Okay.